I'm going to go ahead here and go back through redox reactions and kind of give us a quick overview of what redox reactions look like, including um, electron transfers, assigning oxidation numbers, and those things. Now, redox reactions are reactions in which one or more electrons are transferred. Okay, that's the whole premise of what a redox reaction is. So, for example, sodium and chlorine, if you think about what's going to happen, sodium has one valence electron. Okay, so each atom of sodium has one valence electron that wants to go ahead and give away to the put that negative sign there. So the chlorine. So the sodium is going to give away its chlorine, or give away its electron to chlorine, and then it's going to be happy. So the species losing electrons is said to be oxidized, and the species gaining electrons is said to be reduced. Okay, and so that's that process of giving away electrons being transferred is going to involve redox, and it always happens in pairs. If you can figure out what got oxidized, the opposite is going to be reduced. Now, we've talked about a little bit, types of redox reactions. Really any synthesis, decomp, single replacement, or combustion, electrons are being transferred, and we didn't really focus on this too much until the end of the year last year, but any one of these electrons are being transferred in some way, shape, or form. Now, which then does not leave us much with non-redox reactions. You've got your metathesis reactions, your double displacement or double replacement, and neutralization, which really is just some type of ion rearrangement. So if you just have ion rearrangement, it's not redox, otherwise it's going to be electron transfer. Okay, if you look at the combustion of methane, just to show you where the ions are going to go, or the electrons are going to go rather, carbon is going to lose electrons and oxygen is going to gain them. We're going to talk about oxidation numbers here in just a minute. That's going to explain how that happens and explain how we know that that happens. But if carbon loses them, and since there's no ions present as either reactants or products, but electrons are still transferred. So since they don't all happen in aqueous solutions, we have to have another way in order to reflect how we know that carbon lost electrons and how we know that oxygen gained them, and that's going to be through what are referred to as oxidation states or oxidation numbers. Okay, so this is essentially a bookkeeping of electrons. So it's kind of a construct that we've come up with in order to keep track of where these electrons and these imaginary charges atoms would have in molecules, and real charges in ionic compounds. Okay, we can't really freeze frame it, we're oversimplifying it, but it gives us a way to say it. Now, oxidation states provide a way to track electrons, and they're especially useful in containing covalent compounds that don't have charges. Now, this is a little picky, but when we write charges, we usually write the number first and then the sign. But when we write oxidation states, we usually put the sign first and then the number. Just kind of normal process, or the way that we jot things down, or nomenclature. Now, here are the rules. You've got some more details in your book, more details in Shakashiri if you need it, but I'm going to kind of talk you through some samples. First off, the oxidation state of an atom in an element state all by itself, is going to be 0. Okay, so sodium is 0. Anything that's part of Hunkel fiber all by itself is 0. Mercury, 0. Okay, so if it is all by itself, it's 0. But this is where it's going to throw you. On the flip side, when I mean all by itself, it has to be elemental form. If it is in an ion, it's going to be the same as it's charged. Remember, just in its simple definition, an ion is a charged particle. So if it's charged, it's either gained or lost an electron. So, for example, sodium as an ion that's given away its electron is going to be A+1. Chlorine, or chloride rather, that's gained that extra electron is going to be -1. Nitride would be -3, and calcium would be +2. Also, just as normal writing or nomenclature, we usually write the ions kind of out to the side and the oxidation numbers up above. It's another way to kind of separate it. Some other ones to keep in mind, obviously your alkali metals are all going to be +1s. Your alkaline earths are going to be +2s. You've got your aluminum that's always going to be a +3 if it's an ion. Okay, not if it's all by itself. Zinc is always going to be +2 and silver is always going to be +1. So these are ones that we want to familiarize ourselves in that they won't change. They don't have multiple oxidation states or multiple ions. They only have one charge. Fluorine is always -1. Doesn't matter what it's paired with. It is the most electronegative. So in essence, since it's the most electronegative, it always wins the electron tug of war. And so it always is going to be -1. So for example, again, fluorine here would be, -1. Hydrogen would be +1. Fluorine would be -1. Since there's 3 of them, the whole thing has to equal 0. So phosphorus is going to be +3 to get the whole thing equal to 0. And again, just a reminder on charges versus oxidation states. Oxygen is usually, now we get to some usually rules, usually -2. The exceptions are peroxides, and a peroxide is a polyatomic ion that's O2 with a 2-. In this case, oxygen is -1. So for example, in hydrogen peroxide, you've got H2O2. Oxygen would be a -1. There's 2 of them to get us to -2. The whole thing is equal to 0. So each hydrogen would be +1. And remember that when I do oxidation numbers, I do my math down here. This is what we refer to as the oxidation number for that particular element. Okay, hydrogen is going to be +1 in its covalent compounds. I think last year we simply said hydrogen is usually +1, which is true, but this is a better way to explain it. In some ionic compounds, a metal bonded to a nonmetal, hydrogen can have a negative oxidation state, and that's going to be when it's paired with one of those absolutes. So if you have sodium hydride, remember we already learned that sodium is always going to be +1, so hydrogen then has to be -1 in order to get the whole thing equal to 0. Okay, and then anything else we don't have a rule for. So obviously all of these guys down here are covalent, so hydrogen would be +1 for all of these down here. All right, those are all the rules, so everything else is going to be known from the sums. Okay, everything else is we're going to be able to work backwards. The only other thing, things like transitions, metalloids, typically carbon, silicon, boron will have multiple oxidation states. Nitrogen also is a really common one that we kind of have to work backwards for, typically. And remember, if it's a compound, the entire thing has to equal 0. If it is a polyatomic ion, the entire thing has to equal its charge. So let's just do a couple more together. Here you have carbon dioxide first, a little bit tough to see, so I'm going to actually probably rewrite these here. Carbon dioxide, you will always have a rule for at least one. The rule here is oxygen. Oxygen is usually going to be -2. Since there's 2 of them, it means oxygen's entire contribution is -4. Since the whole thing has to equal 0, carbon has to be +4. So these would be my answers right here. Sulfur hexafluoride, I can get this in here. Fluorine's a -1. There's 6 of them total. So in order for the whole thing to be 0, sulfur has to be, +6. And again, that would be my answer up here. Now nitrate's a polyatomic ion. So the whole thing has to be equal to -1 because it's charge. Because it's going to tell me that right here. If there's no charge on it, then it's equal to 0. I have a rule for oxygen. -2 times 3 is -6. Whole thing it's equal to -1 here. So nitrogen is only going to be +5. And this one's on here just to throw you. Phosphorus, remember, is one of those that we find all by itself as P4. The other exception to that is S8, which would also be 0. All right, now some terms we got to be familiar with redox. Oxidation is an increase in the oxidation state. Okay, so if the oxidation number goes up, it gets oxidized. Well, if the oxidation number goes up, it's because there's a decrease in the number of electrons. And one of the ways that I remember is by LEO is the first part of the acronym, but that stands for lose electrons oxidized, because I think most of us do well with, oh, the oxidation state went up, so it was oxidized. we forget that that's because it's a decrease in the number of electrons. Reduction is going to be just the opposite. If the oxidation state is reduced or it goes down, okay, then the substance undergoes reduction. This is because of an increase in number of the electrons. And the rest of the way that I remember that is with Leo Ger, and that is going to be gain electrons. Well, we're running out of space here. Reduction. Okay, and this is just another way. We do not have to be familiar with the terms reducing agent and oxidizing agent, so you can therapeutically cross those off for right now. But this is just showing you, the one that is oxidized is typically metals. Oxidized also can be another term for rusting, and that usually happens to metals. So metals usually want to give away those electrons. They become oxidized, and then typically the other substance will gain the electrons. Okay, and a lot of times that is the nonmetal. Not absolutes, but some patterns to be familiar with. So if we look at a couple of reactions, we're actually only going to figure out what gets oxidized and what gets reduced, and you can cross off the part on the bottom about the agents. So very simply, I've already assigned the oxidation numbers to these to make it a little bit quicker because I want to point something else out. Aluminum goes from 0 to +3, so it's going to be oxidized. Oxidized. Wow. Okay. Iodide goes from 0 to -1, so it's going to be reduced. Now, just as a remember, if it's oxidized, it means it lost electrons or loses electrons. Reduced means it gains them. Another way that you saw us do what are called half reactions last year was to show actually just the electron transfer. So if I just focus on the electrons being transferred by aluminum, what you have is that aluminum has 3 valence electrons, right? If we think about that from a Lewis dot perspective, and it gives away those 3 electrons to become aluminum 3+. And we have to also represent the fact that the 3 electrons were given away. So anytime you see electrons as a product out here, that's going to tell us that it has been oxidized. And on the flip side, the iodide, and I'm going to start with the I2 here, iodide is reduced. So now this isn't balanced. We're going to get to balancing these later. If I'm going to need 2 electrons because there's 2 atoms of iodide, and what it's going to give me is 2 iodide ions. And again, since they are gaining electrons, anytime you have electrons as a reactant, the substance is reduced. Okay, because Shock is going to walk you through identifying oxidation and reduction reactions as well. Okay, one other example here. You have, and you'll notice there are some things that don't change, and I put this one up here on purpose because if you look at the lead, lead is lead 2 here, and well, it's still lead 2. So although it's part of the reaction, it was not part of the oxidation reduction reaction. Now sulfur went from -2 to +4, so it would have been oxidized. Oxygen went from 0 to -2, so it would have been reduced. Okay, and again, you could write a half reaction showing the electron flow for those as well. Okay, we are going to talk about balancing redox reactions. We're going to do this together in class because I got to walk you through it. This is going to be one of those, another one of these where if you took honors, you may have seen a little bit more of this, but it doesn't mean the rest of you can't do it. But we have to go through another formal process for balancing redox reactions just because it's more complicated. But we'll do that in class. So I hope that